Okay, good. All right, so today let's continue our lecture about sets. So last time we talked about several set operations, the union of two sets, the intersection of two sets, the difference of two sets. And today we're going to talk about another operation. This is called symmetric difference. So what is the definition for the symmetric difference? That is, we put a small triangle between the two sets A and B. So this is called the symmetric difference of A and B, which is defined to be the set of all x's so that x is either in A or B, but x is not in the intersection of A and B. So to write in using our previous notations, the symmetric difference of A and B is equal to the union of A and B, subtract the intersection of A and B. Okay, so if you see the picture, so what is the picture of the symmetric difference for you to understand? Okay, so the picture is if you have a universal set. Okay, this is a universal set U, and you have A, and you have another set B. So the symmetric difference is exactly this part. Okay, so you only throw away the intersection of A and B. So the other parts of A union B are included. Okay, so this is the symmetric difference of A and B. Which is equal to the union of A and B, subtract the intersection of A and B. Okay. Okay, for example, if you look at the set 1, 2, 3 and the set 3, 4, 5, so the symmetric difference of these two sets is simply the union. Okay, what is the union of these two sets is 1, 2, 3, 4, 5. But the intersection of these two sets is 3. So you throw away the intersection, which is a singleton 3. You get 1, 2, 4, 5. And if you look at the New York, Washington symmetric difference with 3, 4, their union is all the 4 elements, but their intersection is empty. So you don't throw anything away. So you get actually the union of these two sets. So the set 1, 2 symmetric difference with the empty set phi. Okay, the union of these two sets is just 1, 2. The intersection is empty. So the symmetric difference is just 1, 2. Okay, so you can see from the last example that the symmetric difference of any set with the empty set will be the set itself. Okay, because the intersection of any set with the empty set is empty. The union is the set itself. So by definition, this is always the case. Okay, so next we talk about the last set operation. This is the complement of a set. Okay, complement sets. So if we have set B, so what is the complement of B? You can see those are just the green area outside B. Okay, B complement, we write B superscript C. B complement is the set of all elements not in B, outside B. Of course, when you talk about the complement sets, you have to designate a universal set U. Okay, the formal definition for the complement of a set is defined to be a complement is equal to the set of all x's for which x is not in A. Or if you use the universal set, a complement is simply U minus A. For example, if we let the universal set U to be the set of all integers Z, then the set A is equal to 1 to 3. Then a complement is simply all the integers except 1 to 3. So that's very easy to understand. Okay, so there are some basic properties for complement sets. The first one is if you look at the set A and its complement, A complement, if you take the complement of A complement, it comes back to A. So this is obvious from definition, okay? The complement of A complement is just A. And the second is the union of A and its complement is the universal set, okay? Because you put the elements in A and the elements not in A, then that means all the elements in U. The third one is A intersect A complement is empty because A complement contains no element from A, so the A and A complement doesn't share any element, so the intersection is empty. So those are basic properties we should keep in mind, and later when we want to prove some set equality or set inclusion, you need to use those basic properties. Okay. All right, now let's come to the main question for set theory. So the question is how to prove two sets are equal. How should we prove two sets are equal? Because two sets may be described in different ways. So it looks from their appearances, they're different. But if we want to show they're actually the same set, how are we going to prove this? So the procedure is the procedure is, so say we first prove one of the sets, say A, is a subset of B. So this means what we want to show, that is take for any element say X in A, we show that X is in B. Okay? If you prove that any element of A is an element of B, then you proved A is a subset of B. And then second, we prove B is a subset of A. Okay, once you prove these two results, then you can claim, then we get A equals to B. Okay, so whenever you want to prove two sets are equal, you should follow these two steps. First, you show A is a subset of B, and then you show B is a subset of A. And once these two conditions are shown, you can claim A is equal to B. Okay, let's look at an example to see how we execute this method, this procedure. Okay, so the first problem is a theorem. So let A, B, C be sets. Then we want to prove two things. The first one is A union B intersect C is equal to A union B intersect A union C. And the second is A intersect B union C is equal to A intersect B union A intersect C. Okay, we want to show these two results. So proof of one. Okay, let's first we want to prove the left-hand side, that is A union B intersect C, is a subset of the right-hand side. And then we want to show the right-hand side is a subset of the left-hand side. So for this one, so first, we show A union B intersect C is a subset of A union B intersect A union C. Okay. How to prove this? So we'll let X be any element, X being an element in this set A union B intersect C. And we want to show this X is contained in A union B intersect A union C. So we have to use definition. So X is in the union. Remember, what is the definition of union? The union means X is either in A or in B intersect C. So X is in A, so this is by definition, or X is in B intersect C. Definition. So we should look at this both cases. So if X is in A, so if X is in A, then of course X is in A union B. Okay, because A union B is larger than A, it contains both the elements in A and both elements in B. And similarly, X is also in A union C, because A union C is larger than A. Hence, by definition, this time, because X is in A union B and X is and, so you should remember, and X is in A union C, this means, by definition, X is in the intersection of these two sets. X is in both sets, which means X is in the intersection. Okay, so you see each step we use definition. So you have to be rigorous what is the reasoning behind your conclusion. Okay, so this finished the proof of the first step. We showed that A union B intersect C is a subset of A union B intersect A union C. Okay, so the second step, we show A union. Oh, I haven't finished this. I'm sorry. So you should remember, we only considered one case here. We only considered, because we only assume X is in A, but we have two cases here, X is in A or X is in B intersect C. So we have to consider the second case. So if X is in B intersect C, then what we can say is then, by definition, X is in the intersection means S is in both sets. So X is in B and X is in C. Okay, if X is in B, so what we can claim is X is in A union B. Because A union B is larger than B, X is an element in B, of course X is an element in A union B. And similarly, X is in C, so we can get X is in A union C, because A union C is larger than C. But then, by definition, X is in both A union B and A union C, hence X is in the intersection of these two sets. Again, definition. Okay, so you can see all those steps uses definitions. So these two arguments tells you, you take any element in A union B intersect C, you show that this element is always in A union B intersect A union C. So the first step is finished. So now let's look at the second step. So we show that A union B intersect A union C is a subset of A union B intersect C. Okay, how to prove this? We take any element, so let X be any element in A union B intersect A union C. Again, by definition, X is in the intersection of these two sets. That means X is in A union B and X is in A union C. Okay, so let me copy down this translation to the next page. So what we get is actually X is in, so we get X is in A union B and X is in A union C. Okay, so look at the last statement. X in A union B and X in A union C. Okay, so we have to explain what is this. So X is in A union B means X is either in A or in B. Okay. X is in A union B implies X is in A or X is in B. Okay, now we just look at two cases. So case one is if X is in A. So if X is in A, what we have is, of course, X is in A union B intersect C. Because A union B intersect C is, of course, larger than A. You union something with A is larger than A. But then this is already what we want. This is okay. Okay. If X is in A, we are obviously fine. This element is going to be in A union B intersect C. So the second case is if X is not in A. Okay, if X is not in A, look at here. Because X is either in A or in B, if X is not in A, then X has to be in B. Then X has to be in B. And similarly, since X is in, so here, A union C, X is in A or X is in C. But because X is not in A, so remember we are in the second case, okay? We are in the second case. But because X is not in A, then X has to be in C. So what we get is X is in B and X is in C. So X is in B intersect C. And hence, if we union A with it, then hence X is in A union B intersect C. Okay, because X is already in B intersect C, when you union something else, it's certainly true. So you can see in either case, case one or case two, you get both that X is in A union B intersect C. Therefore, so now we can claim, because we proved both the inclusion, therefore A union B intersect C is equal to A union B intersect A union C. Okay, so do you have any questions? Okay, so this proof is very rigorous. Okay, so you have to be very careful about the definitions of each step. All right, now let's come back to the second statement we want to show. That is A intersect B union C is equal to A intersect B union A intersect C. So let me start start a new page. Okay, so the second thing we want to show is we want to show A intersect B union C is equal to A intersect B union A intersect C. Okay, again, we are going to prove this by two steps. So first, we show that A intersect B union C is a subset of A intersect B union A intersect C. Okay, to prove this, we take any element x in the left-hand side, A intersect B union C. We want to show x is containing A intersect B union A intersect C. So what is the meaning of this? This means x is in A because this is intersection, and x is in B union C. Okay, B union C. All right, so we have to keep explaining this. This implies x is in A, x is in A, so this implies x is in A, and okay, let me put a parenthesis. So x is in B, or x is in C. Okay, x is in the union of B and C means x is in B or x in C. So actually there are two cases, x is in B or x in C. So we should look at both cases. So if x is in B, then because x is always in A, you should remember, because this is x in A and x is in B or C. So x is always in A. Then x is in the intersection of A and B. So x is in A intersect B union A intersect C. Because you are adding A intersect C to A intersect B, so x is still in the larger set. Okay, the second case is if x is in C, again, because x is always in A, then you can get x is in A intersect C. So we again get x is in A intersect B union A intersect C. Okay, because this set is larger than A intersect C. So in both cases, we get x is an element of A intersect B union A intersect C. So the first thing, this one is proved. Okay, now let's look at the second step. The second, we show A intersect B union A intersect C is a subset of A intersect B union C. Again, we'll take any element x is in A union B union A intersect C. Okay. So what is the meaning of this? This is a union. So that is X is in A intersect B, or X is in A intersect C. Okay, so we should look at these two cases. So if X is in A intersect B, then X is in A and X is in B. But if X is in B, then so X is also in B union C. Okay, B union C is larger than B. And okay, remember X is in A, so you get X is in A intersect B union C. Okay, this is the first case here, if X is in A intersect B. So we have the second case, X is in A intersect C. So if X is in A intersect C, then again, we get X is in A, or X is in, not or, and. Okay, and X is in C. So hence we have, since X is in C, X is in B union C. Now X is again always in A, X is in B intersect union C. So X is in A intersect B union C. Okay, so in both cases we showed the this X is in A intersect with the B union C. So therefore, so we can claim, therefore, these two sets are equal. So A intersect B union C is equal to A intersect B union A intersect C. Okay, so these two identities are very useful. So you should memorize those identities, because you are allowed to directly use these identities in your exam or homework. Okay. So you can see from these two examples, the proof of two sets are equal essentially follow these two steps, and each step, each argument you use is from definition. So definitions are essential for this for the proofs in mathematics, especially in set theory. Okay, do you have any questions? Okay, so we don't have questions. Let's proceed to some simple facts. This is again a theorem. So let A, B, C be sets Then we have the following three things. So if A is a subset of B and B is a subset of C, then A is a subset of C. So this is a transitivity, okay, for sets. And this is a simple fact. We don't want to prove. So the second is A union B is equal to A if and only if B is a subset of A. So well-proved number 2. And the third one is A intersect B is equal to B if and only if B A is a subset of B. Okay, so no. This is in the section. B is a subset of A. Okay, well, proof 2 and 3. The first one is easy. You can verify by yourself. So let's look at how to prove proof of 2. So we'll prove these two things, but if and only if. To prove if and only if statement, you have to prove two directions. You first assume the first condition, you will show the second statement. Then you assume the second statement, you show the first statement. So to show if and only if, so this direction means suppose A union B is equal to A, and we show B is a subset of A. So this means this direction. Okay, so this uses definition. So we just use this condition, A union B is equal to A. But what we want to show, B is a subset of A. How to show B is a subset of A, which means we take any element in B, we show that element is also in A. Okay, we'll just let X be in B. Okay, then by a simple fact, we know that X is in A union B, because A union B is larger than B. But use this now, we can use the condition now, since A union B is simply A. This is our condition assumption. So what you can claim is X is in A. Because X is in A union B, but A union B is just equal to A, so X is in A. So now you can see we take an X in B, we show that X is in A. Okay, we finished the proof of one direction. Now we want to prove this direction. So this direction means, suppose B is a subset of A, and we show A union B is equal to A. Okay, suppose B is a subset of A, we want to show A union B is equal to A. Remember how to show two sets are equal. We have to show two identities, That is, the first one is A union B is a subset of A, and the other is A is a subset of A union B. But one direction is easy because A is always a subset of A union B. We only need to prove A union B is containing A. Okay, so to prove A union B is containing A, we just take an arbitrary element in A union B. We want to show that element is also in A. So we'll let X be in A union B. Then by the definition is X is in A or X is in B. Now we have to use our assumption here. B is a subset of A. Since B is a subset of A, the second condition implies since B is a subset of A, X in B still implies X is in A. So in this situation, although you have seems like you have two choices, X is in A or X is in B, but in either case, X is always in A. So X is always in A. So therefore, you prove two directions, therefore, A union B is equal to A. Okay, so to prove an if and only if statement, you have to go both directions. Okay, and maybe in the proof, you also have to consider two steps because you want to prove two sets are equal, then two inequalities, two inclusions that need to be verified. Okay, so this is 2, and next we show 3. So A intersect B equals to B if and only if B is a subset of A. Okay, let me write down number 3 in the next page. So 3 is A intersect B is equal to B if and only if B is a subset of A. Okay, again, the proof. So you first go to these directions. We want to suppose A intersect B is equal to B, and we show B is a subset of A. All right, so to show B is a subset of A, we'll let X be any element in B. We want to show X is in A. So to show this, we use the hypothesis A intersect B is equal to B. So then, okay, so I should say since A intersect B is equal to B, so we get X is in A intersect B. So in particular, this implies then X is in A. Okay, because x in A intersect B means x is in both A and B. In particular, x is in A. Okay. All right. So this direction is very easy. All right. So we have B is a subset of A. Okay. This is one. So now let's look at this direction. And suppose B is a subset of A, and we show A intersect B is equal to B. So to show two sets are equal, we have to show two inclusions. But one inclusion is already there because A intersect B is always a subset of B. A intersect B contains all the elements both in A and B. In particular, all those elements are in B. Okay, since it's obvious that A intersect B is always contained in B, so we only prove B is containing A intersect B. So to prove B is a subset of A intersect B, we'll let X be any element in B. Now we use the condition since B is a subset of A. So, okay, since B is a subset of A, B is a subset of A, then X is in A. Now X is in both B and A. So we have X is in A intersect B. So that is B is containing A intersect B. Therefore, A intersect B is equal to B. Okay, so you showed both directions.
I have a question.
Yes.
Is this sort of like subjective?
Well, what do you mean in your language? What do you mean by subjective?
Where if I find X in A, I can find it that it maps to B.
No, well, in this case, it doesn't mean it maps. I have to show the exact element is in B.
So okay, so the same element.
The same element, okay? So when you talk about sets, B is containing A, you have to show the exact element is also in the other set. It's not a map.
Okay, that makes a lot more sense what you're doing now. Okay.
Yeah. Okay. All right. So next we talk about the famous law in set theory that is called the De Morgan's laws. Okay. De Morgan's laws. So the first one is A taken away, B intersect C is equal to A taken away B union A taken away C. The second is A taken away B union C is equal to A taken away B intersect A taken away C. Okay, so sometimes this De Morgan's law is written in a different way. For example, so here, so remark. If we take A to be the universal set, then what is the meaning of A taken away B intersect C? Then A taken away B intersect C in our notation would be B intersect C complement. All right. So A is a universal set. A minus B intersect C is a set of all elements which are not in B and C. B intersect C. So it's just B intersect C complement. And we know that A minus B is just B complement, and A minus C is C complement. Morgan's law become the following. That is B intersect C complement is equal to B complement union C complement. So this is the first. And the second one is B union C complement is equal to B complement intersect C complement. Okay, so you may see this form is more commonly used. However, this theorem, the theorem here is more general because this is for any set A, okay, any set A. You see, they are essentially the same, but formally is more general, okay? Because when you talk about complement, you always designate a universal set. But in that form, you don't designate the universal set, but essentially A serves as the role of the universal set. All right, so let's prove, try to prove De Morgan's laws. So let's write the first De Morgan's law in the next page, and then we'll start proving one, and then we'll prove two. Okay, so the first one we want to prove is A minus B intersect C is equal to A minus B union A minus C. So to prove two sets are equal, so we want to show two things. one set, the left-hand side is a subset of the right-hand side, and the right-hand side is a subset of the left-hand side. Okay, so let's look at the proof. So first, we show A minus B intersect C is a subset of A minus B union A minus C. To show one set is a subset of another, you want to take an arbitrary element in one set. So let X be in A minus B intersect C. You want to show this X is in the right-hand side. Okay, so we have to explain what is the meaning of X belongs to A minus B intersect C. So this means X is in A, but X is not in B intersect C. Okay. So X is in A, but X is not in B intersect C. All right, so, but what is the meaning of the second one? The first one is easy. X is in A is clear. But what is the meaning X is not in B intersect C? So to understand this statement, you first have to recall what is the meaning of X belongs to B intersect C. X belongs to B intersect C means X belongs to B and X belongs to C. So if X is not in B intersect C, that means X must fail one of the two conditions. That is, X is not in B or X is not in C. So what we can claim, so X is not in B or X is not in C. Okay. Okay, so if X is not in B, because X is always in A, then this means X in A but not in B, then you can get X is in A minus B. So this is definition. So what we can claim, X is in A minus B union A minus C. Okay? Because this is a union of A minus B, and A minus C is larger than A minus B. And the second case is if X is not in C, again, because X is always in A, then X is in A minus C. This is by definition. So X again is in A minus B union A minus C. Okay, in either case, you get X is contained in the right-hand side. Okay, so the first step is proved. We proved that A minus B intersect C is a subset of A minus B union A minus C. Okay, the second step is we show A minus B union A minus C is a subset of A minus B intersect C. Again, we take an arbitrary element, X be in A minus B union A minus C. So by definition, X is in the union means then X is in A minus B, or X is in A minus C. So X is, so we have two cases. So you have to look at the two cases. So if X is in A minus B, then X is in A and X is not in B. This is the definition of A minus B. But if X is not in B, certainly X is not in a smaller. So X is not in a smaller set. X is not in B intersect C. Okay, because B intersect C is smaller than B. X is not in a larger set, so X is not in a smaller set. Remember, oh, this is not A in A, this is X in A. Okay. X. Because X is always in A, hence X is in A minus B intersect C. Okay, because X is not in B intersect C, but X is in A. By definition, X is in A minus B intersect C. Similarly, if X is in A minus C, then X is in A and X is not in C. So again, X is not in C, then X is not in a smaller set, B intersect C. And hence, X is in, because X is always in A, so X is in A minus B intersect C. So we proved the first left-hand side is a subset of the right-hand side. And second, we proved the right-hand side is a subset of the left-hand side. So we can claim, therefore, these two sets are equal. Okay, so this is the first statement of De Morgan's laws. Well, this is just like playing with concepts, definitions. So you can prove that the proof was for this set theory mostly just playing with the definitions and elementary logic. So any questions about this first proof here? All right, so let me prove the second one. So after I finish the second proof, then I'll let you go because today is very, I think it's very intensive, so you must be very tired. Okay, let's look at the second one. So we want to show that A minus B union C is equal to A minus B intersect A minus C. Again, we'll follow the two-step proof. First, we want to prove the left-hand side, A minus B union C is a subset of A minus B intersect A minus C. Okay, to show one set is a subset of another, we take an arbitrary element of the first set. So let X be in A minus B union C. We want to show X is in A minus B intersect A minus C. So X is in A minus B union C by definition. Then we get X is in A and X is not in B union C. Okay, so X is not in B union C. So this is the most important thing we have to explain, interpret. So X is what first we have to think about what is the meaning of X belongs to B union C. X belongs to B union C means X belongs to B or X belongs to C. Then X does not belong to B union C means X cannot belong to B and X cannot belong to C. In other words, this condition tells us X is not in B. Okay, you have to be careful here. This means and X is not in C. So this is the key step you have to explain. Okay, X is not in B union C means X is not in B and X is not in C. All right, so remember X is always in A, hence by definition, X is in A minus B. Because X is in A, but X is not in B, means X is in A minus B. And because X is in A, but X is not in C, then we have X is in A minus C. Now we use definition again. X is in A minus B, and X is in A minus C. So X is in the intersection. Okay, so we proved the first step. So A minus B union C is a subset of A minus B intersect A minus C. Now the second step is to show the right-hand side is a subset of the left-hand side. So second, we show that A minus B intersect A minus C is a subset of A minus B union C. To show this, we take any element X in A minus B intersect A minus C. X is in the intersection. That means X is in both sets. So X is in A minus B and X is in A minus C. Okay, X is in A minus B and X is A minus C. So what we get is the first condition X is in A minus B. We get X is in A and X is not in B. Here, the second condition is X is in A minus C, that is x is in A, and x is not in C. So you should look at all those conditions. Every conditions are AND, which means x has to satisfy all of the conditions. X is in A, x is not in B, and x is not in C. Now we just use these two conditions, x is not in B, x is not in C, and what we get is x is in A, this is for sure, and x is not in B union C. Okay, because x is not in B and x is not in C means x is not in B union C. So you can claim x is in A, x is not in B union C means x is in A minus B union C. So this shows that A minus B intersects A minus C is a subset of A minus B union C. Okay, we finished the proof of these two steps. Therefore, A minus B union C is equal to A minus B intersect A minus C. Okay, so this finishes the proof. So you should remember when you work on problems for set theory, please follow rigorously those procedures. Okay, you have to show one set is a subset of the other, and the other is a subset of the original one. Okay, every step you have to ask yourself, what is the reason there? Why you claim this is true? So you can't only use intuition. You have to use rigorous logic to verify your argument. Otherwise, it's very easy to cheat in the proof for set theory. Okay, so do you have any questions? All right, so I'm gonna assign the fourth homework late tonight. So please check back tomorrow. And this time the due date will be next Tuesday, not next Tuesday, the week after next, the Tuesday after next, which you'll get 1 week and a half to finish because some of the problems may be more time consuming. All right, so if you don't have any questions, we'll stop it here today and see you next week.
Thank you.
Yeah.